Welcome to the CFE Media and Technology Education Session, Developing a Great Sequence of Operations. I'm your moderator, Mark T. Hosky with CFE Media and Technology. In keeping with our CEP policy, please take some time to read the quality assurance slide. This session is designed for technicians and engineers who want to examine all the parts of a sequence of operation, including considerations of what makes a good sequence of operation and how transfer switches could be prioritized based on code and operations of the system. Here is a list of learning objectives for this session. We'll touch on these in today's presentation. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. For a seamless online experience, here are some tips. Additional resources can be viewed and downloaded on the left side of the screen below the session's agenda. If you would like to take notes within the session, click on the left panel labeled Notes to do so. This session is available on demand if you need to come back at any time. Please remember that this session will be made live at 2 p.m. Central and 3 p.m. Eastern, with a Q&A starting at approximately 2:45 p.m. Central and 3:45 p.m. Eastern, or immediately after the presentation ends if it runs a little longer than 45 minutes. Industry experts will answer viewer questions live, and those answers will be archived with the session. You can see the Q&A details in the Meetings tab on the left side of the screen. Here is some information about obtaining an approved PDH for today's session. Before I introduce today's speakers, we'll have a brief video from our sponsor.
We're all thinking about our hands, and right now, we'll need them more than ever. America's vital factories, power plants, data, water, waste, national security, hospitals, all need people on the ground to keep them functioning. Because our technology is only as powerful as the people deploying and maintaining it. It takes a human touch.
Today's speakers are Jeremy Gustafson, Business Development Manager, and Zach Goldsworthy, National Healthcare Market Leader, both with Siemens Industry Incorporated. I'm your moderator, Mark T. Hosky, Content Manager, CFE Media and Technology. Next, a little more about each speaker. Jeremy Gustafson is driving Siemens business development opportunities for electrical power distribution products in the upper Midwest, with a primary focus on technical and product support for consulting engineers as well as electrical contractors. Prior to joining Siemens in 2014, Jeremy spent 16 years on the consulting, engineering, and construction side of the industry. His background in electrical design and construction offers him insights in supporting the consulting engineering community. As a national healthcare market leader, Zach Goldsworthy designs cost-effective electrical engineering solutions that provide high-quality outcomes in the healthcare design field for healthcare facilities in the United States. With more than 10 years of experience in the healthcare and higher education construction field, he applies a strong engineering background to develop engineering solutions that meet clients' needs for safe, efficient, and reliable power supply systems. Jeremy and Zach, thanks for joining us. Please go ahead with your presentation.
Well, thank you, Mark, for the great introduction. And we are very pleased to be here, part of this virtual week of training. And we really hope that everyone participating finds these courses valuable. Today in this session, there are many objectives that we are working through, as Mark discussed, and we will be working through those one at a time. As far as one line, we're going to take a look at some key terms. With that, there are some load classifications that we need to differentiate and understand so that we're all on the same page. There are some considerations within the system design that we will be discussing. And as far as When we lose power, we will discuss some intent options and what our options are when that happens. One fun part, we'll actually dive into an example with the Level 1 Trauma Center, and then follow up with some best practices, some lessons learned, and a commissioning review. Don't pay too much attention about all the details on this one-line diagram. It's just to give a quick overview of the system that we will be discussing. In the pink highlighted areas of the paralleling gear, that is a primary focus of what we'll be discussing and where the brains of the sequence of operations resides. That is the paralleling switchgear for the emergency system. In the teal, you'll see transfer switches along with the auto throw over breakers. And again, these are differentiated depending on whether they are life safety, critical power, or equipment in this healthcare example. One thing to note with a sequence of operations is they are very unique depending on the project, and everyone is customized for the project that it is driving. First thing we want to talk about with the load classifications is the load types. First of all, we want to talk about healthcare as defined by IBC I2 and NEC 517. The key terms in this slide are life safety branch, critical branch, and equipment branch. In contrasting that with non-healthcare, we'll call this mission critical for the sake of this discussion on sequence of operations. And differentiating healthcare from non-healthcare, we'll talk about emergency as defined by NEC 700, legally required standby as defined by NEC 701, and optional standby.
As Jeremy laid out, the sequence of operation identifies how the transfer switches and parallel switchgear operate and primarily come onto the emergency mode. Prior to developing the sequence of operation, there are a number of system design considerations that should be evaluated. This would include the generator sizing compared to the redundancy. For example, there are multiple combinations of generators to get to a 4 megawatt capacity. Note that different sizes have different footprints and potentially separately mounted radiators, impacting the layout and the configuration. Adversely, it's important to size the generators in a manner where possible that the generator can carry all of the emergency Article 700 loads. We'll dive into this more in detail in a few minutes. Additionally, although the ATSs and parallel switchgear have the ability for many different functions, such as peak shaving, it's important to remember the generators have tier ratings, which are determined largely by their NOx emission levels. It's also worth mentioning that it varies county to county, but many of the counties have permits that determine their operation time. And of course, when a facility loses power and the generators are on an emergency mode due to utility power loss, this does not count as hours on their permit, as long as it's documented. Briefly, on existing conditions, it's important to make sure that the controller, which is integral to the generator, is sufficient for the paralleling capability, and that the generators also have the same pitch, whether it's 2/3 or 4/5. Before we dive into the sequence of operation, it's important to understand what operation is already programmed into the generators. First, as soon as the generators are connected to the emergency bus, the generators automatically evaluate the load. From here, they actually balance the load to load up the generators from 50 to 80% of their rated capacity. They then disconnect the unrequired generators based off this loading. But it is worth mentioning that this is actually different for different classifications of generators, whether it's natural gas versus diesel. Also, it is important at the beginning of the project to review the submittals and ensure that the generators have the transition runtime programmed into it, which allows the generators to spread the hours across each of the generators. So for instance, if you have an n+1 redundancy, generator, for instance, 4 is not always a redundant generator and thus not being utilized. We want to make sure those hours are spread evenly as possible across those operations. Additionally, if a generator does fail, whether it's due to maintenance or an emergency condition such as the turbo starting on fire, it automatically disconnects from that emergency bus. Additionally, that overload operation, generators are built in with the capability of temporarily being overloaded, but as soon as that does get in, that load gets shed, and we'll get into that more here in a few minutes. And then finally, when the transfer switches go back to the normal source, the generators go into the cool down automatically, which is typically 15 minutes, but again, this is pre-programmed into the functionality of the generators. When we look at the sequence of operations developed, we want to make sure we're looking at the system holistically. So for instance, when we look at the percentage of fuel being utilized, we want to make sure we understand that along with the consumption rate of the generators and the anticipated demand of the load. And we want to make sure at a certain percentage, it alarms to the facilities team to make sure that fuel delivery is coordinated. And if it's not done in a certain amount of time, then at a lower percentage, the system starts to shed load if that's necessary for an extended outage. From a generator failure, we'll touch on in a few minutes some of the failure modes, but when a generator fails, the generator circuit breaker opens, the parallel switchgear reviews the load, and then drops the lowest priority until that demand, again, does not exceed that generator capacity. This comes from the prioritization of the transfer switches that we'll get into in a few minutes. One of the things we'll examine as well is how does our priority changes as the seasons of the facility also change. It's important to understand and consider the fact that the mechanical systems region to region are different for the impact of the facility. Obviously, the cooling in the south is equally as important as the heating in the north. But we have to make sure we always design this in a code compliant manner, and that heating is required by code to be on the equipment branch.
So before we get into the details of the intent of the sequence of operations, let's do a high-level review of a typical process. Step 1, we lose power in the building, typically from our utility normal source. Step 2, the generator receives a start signal from the transfer switches. In step 3, once the generators are started, the transfer switches switch over to an emergency position based upon the predetermined priority. In step 4, the system maintains an alternate source status. Going into this in further detail, the first question that we ask is, what is triggering the event? Typically, they would fall under a full loss of power or a voltage variation outside of what we would like to see for our normal voltage. Step 2, the generators are initiated a start signal by the transfer switches. The transfer switches are obviously monitoring the power status and the integrity of the power that's coming in. A couple different ways that this can be done is the generators hit the bus with the load, or the generators parallel and then close and the load is transferred over. Step 3, the life safety and critical load transfers over within 10 seconds, or in a non-healthcare facility, the emergency load would transfer over within 10 seconds. Moving on to step 4, the equipment transfers in stages, and this can be determined by priority of the equipment that they want to see on that, and we'll talk about that in a little more detail in a little bit. And lastly, the optional standby transfers in stages, again, based upon priority and availability of generator power.
So next, we're going to examine what makes a good sequence of operation, which includes reviewing the location of the site as it relates to the climate and access to the fuel for the generators. Then we're going to start to dive in understanding the operation, as well as make sure we understand and provide a preliminary load scheme that can be evaluated for the project. So the different sequence of operation modes for the parallel switchgear are as follows. The normal operation, which will maintain about 99% of the equipment's life, depending on how often utility outages occur or depending on the functionality of the system. Second is when we utilize or have a loss of normal source. And then we'll look at two different retransfer sequences, one open and one closed transition. And then we'll also start to examine what the failure modes are. So if a failure does occur in the unlikely event, the equipment is programmed to respond accordingly. And then if any of those failures does impact the capacity of the generators, what load potentially would need to be shed, followed by maintaining the system and providing all of the required testing, including the load bank and then the generator testing. So we're going to look at applying this in an actual specific example. The example we're going to examine is a level 1 trauma center. And for the example, 550 bed medical center, 18 operating rooms, and 8 stories. A facility like this, we'd expect multiple generators and a couple different transfer switches for each of the branches. In this example, we have 5 generators of different sizes and installed in different years. During the evaluation stage, the emergency paralleling switchgear has the loads defined as such. Priority 1 and 2 loads are a combined 1600 amps, and priority 3 loads is a combined 1500 amps, followed by the priority 4 or the optional standby load of 500 amps. Hopefully many of you have already identified that the capacity or the load for priority 1 and 2 exceed the amp rating for 2 of the generators listed. So first, looking at the sequence of operation in the normal mode, the equipment operates de-energized. The branch circuit breakers will be closed and the generator circuit breakers will be open. And again, this is the regular operation of the equipment as it stands in a ready state for a normal source power loss. So now we're going to look at how the equipment reacts when that loss of normal power happens. After the loss of the normal source, the generators receive that signal from the transfer switches, signaling the generators to start. At the beginning, all 5 generators are programmed to be started. From here, we want to make sure that the first generator online can carry the full load of the priority 1 and 2 transfer switches going into the emergency position. As such, the first generator over 1000 kW that hits the bus will carry that load. We want to make sure, although the 500 kW engine generators may start quicker, that we have the first generator over 1000 kW carry that load. And this will allow the system to do it within 10 seconds of that normal source being lost. At that time, that first generator coming online, from there, the remaining generators come online and the associated generator circuit breakers close. From here, the priority 3 transfer switches go into the emergency position and are being energized. At this time, the generators complete an automatic load analysis for the additional load from priority 4 to come online. Although in our assessment on the previous slide, we showed that the generator capacity can support this, the system wants to evaluate that all the generators online and that capacity is available, that nothing is down from a failure or from maintenance. As soon as that load capacity from the generators is confirmed, the priority 4 transfer switches will go into that emergency position. At this time, the generators will complete that load analysis again, and now, however, it will disconnect any generators, so the remaining generators are at a 50 to 80% load for all the generators are connected. And this is to prevent wet stacking and damage to those generators, as well as their ideal fuel consumption in operation. Now that we know how the equipment operates at a utility or normal source loss, we want to look at how the equipment is retransferred. And we want to start with a closed transition example. So quickly, a closed transition means that when the equipment goes from emergency source to normal source, there is no interruption in power. This is something that's very important to coordinate, not just with the facility, but also with the utility company and any end user in terms of operational impacts. It's also important that the transfer switches that are existing are identified and reviewed, that their functionality is built into this. And we'll touch on that in a second. But upon sensing the failed normal source being restored for 15 minutes of continual power at that rated voltage, the retransfer sequence is initiated and that automatic synchronizing of the generator bus is initiated. It is important to mention that that 15 minutes of continuous power at the rated voltage is programmable. 15 minutes is typical. However, it can be shorter or longer based, again, off the utility's requirements or the facility's request. After that's complete, synchronizing is verified across the transfer switches, the life safety, the critical, and the equipment in a hospital application. Many of you know that NFPA 99 requires transfer switches for the life safety, critical, and equipment branch, and that the optional standby branch can actually be done utilizing circuit breaker interlocks. In this example, the optional standby is being done with circuit breakers, in which case the load is transferred back to the normal source, and that synchronizing is verified across the circuit breaker. It's important to identify that the closed transition operation in this example will occur in less than a second or 60 cycles. This, again, is something that needs to be verified by the utility company and ranges based off of each of their specific design requirements and parameters. At this time, all of the transfer switches are back in their normal source and the generator circuit breaker are open. From here, the generators proceed into their program and the controls are automatically reset and the generators are placed in readiness for the next power interruption. At this time, the system is returned to normal operation where the generator circuit breakers are open, the branch circuit breakers are closed, and again, the generators are sitting in readiness. Now we'll look at that same sequence of operation in an open transition sequence. In an open transition sequence, we will see that interruption from emergency source to normal source. Although it will only be a brief second, it is worth mentioning that any computer or data loads will be interrupted. So again, in the same sequence, upon sensing that failed normal source being restored for 15 minutes, again, programmable, at that rated voltage, the retransfer sequence is initiated, and this automatic synchronizing of the generator bus is initiated. There is no synchronizing across any of the transfer switches or any of the circuit breakers. All of the transfer switches go from normal to emergency source, and that interruption occurs. From here, that generator circuit breakers are opened, and again, the generators, similar to before, proceed into their program cooldown and are automatically reset and placed in readiness for the next power interruption. And again, at this time, the system is returned to its normal operation.
All right, nobody likes to talk about when something might go wrong, but a sequence of operations wouldn't be complete with discussing of how we might address a situation if something did fail. Now, with any of these failures that we are discussing, they're all very rare, but we still need to discuss what we might do. This first one we'll look at is related to a failure of paralleling switchgear PLC. In the case of a single PLC failure, we are confident that the redundant PLC processor would be available to pick up that operation and control the switchgear. In the case that both PLCs failed, the system operation would alarm and a facilities team would be brought to their attention to take over it and operate it manually. In the case of a failure of a generator circuit breaker, which again would be very rare, the system would again alarm and notify the facilities team for them to get involved and resolve the situations. Once the transfer switches are signaled and back in the normal source position, the generator would go down to its normal programmed cool down. Another failure that we want to talk about is a failure of a transfer switch. And if the transfer switch is in the emergency position or the normal position and not able to switch one way or the other, again, if the generator, if it was in the emergency position, would remain energized to support the loads that are on the bus. In either case, the system would alarm and again notify the facilities team for resolution of this so that they can get involved and handle the situation manually if needed.
So next, we want to look at a proposed load shed scheme. When examining how this system can shed the load, it can be done either through the circuit breakers within the parallel switchgear or through signals sent to the transfer switches. The transfer switches are signaled to disconnect from the emergency position until the load does not exceed the capacity of the emergency bus, and it starts with the lowest priority. Again, although similar to what Jeremy mentioned on being very unlikely, similar to the load shed, we want to make sure the system is programmed to operate in any condition, no matter how many failures happen, to ensure the most potential operation of the facility can be done. So to begin this process, we want to list off each of the transfer switches by priority. Life safety, obviously first, critical, second, and equipment branch designating a separate priority for each of those transfer switches. Earlier, we mentioned that it's important that the transfer switches and the generators can support all of the priority 1 and priority 2 loads, meaning, as shown here, the life safety and the critical loads. In the event that, say for instance, in the example, all the generators fail except one of the smallest ones that cannot fully support that load, it is still important in best practice, although it can never be done except when generators fail, that all of the transfer switches still have a priority designated to each of them. So again, when we look at what this means from a facility and identifying a proposed priority, life safety, priority 1. Critical being priority 2. And we look at the critical branch, we start the highest priority of the critical branch, starting with the spaces serving the highest level of acuity. So first, the transfer switches serving anything within the anesthesia spaces, such as the ORs. It's important to mention that a critical branch transfer switch could serve multiple different spaces, such as the ORs or a piece of imaging equipment. In this case, it's important that all of the feeders from that transfer switch are designated by their highest level of acuity, in which case that example would be classified under the anesthesia and therefore part of the 2.1 proposed priority. From there, we'll go down to the next level of acuity, to critical care as defined by 517, being category 1, including an ICU, a CCU, or a NICU. Additionally, from there, the general care or category 2 spaces, followed by the imaging modalities. It's very common in a healthcare environment that the imaging modalities are broken up into 2 transfer switches. First being the invasive imaging modalities, such as an angio, EP, or CT, then followed by the non-invasive modalities, such as an X-ray, a fluoro. And these spaces have, again, based off the acuity, we want to make sure that the invasive transfer switch is higher priority. And although those systems commonly have a UPS, whether it's a flywheel or battery, they only carry it from 10 seconds to a couple minutes. So it's important that those are still on that higher priority. From there, we look at the spaces and the systems serving non-patient spaces, but still critical to operation, such as the pharmacy, the lab, the blood, bone, and tissue bank, followed finally by the IDF rooms, if they're separated. Again, this is proposed and should be examined part of each project, but does provide a guideline and recommendation. Finally, when we look at the equipment branch priority, we again look at it as spaces or equipment that serves a higher level acuity. First, starting with anything associated with a medical vacuum or medical gas. Obviously, this would be directly associated with the patient spaces, followed by any sump pumps or alarm. And then next proposed is 3.3. We get into any of the compressed air serving equipment or surgical functions like cleaning. And then this gets into followed by the smoke control and stair pressurization, followed by the mechanical system. The mechanical system, it's important to consider holistic prioritization of the system. So for instance, if you have an air handler, it is important that the cooling tower, chiller, and pump associated with maintaining that, along with the control circuits, are also identified as a higher priority, equal to make sure that operation for that space could be maintained. From there, it would also include the heating system, and then cooling system, if there's any redundancy, followed finally by the kitchen and any delayed egress. When we look at the load bank, there's actually no sequence of operation that's required for this. For everyone on the call, it is important to identify that the load bank is done by connecting a load bank that typically is brought to the facility. From here, this load bank is connected to each of the generators. If there's no provisions, such as cam locks, for this load bank, that generator needs to be disconnected from that emergency bus for that load bank to be accommodated. So it's important that this discussion is had with the facilities team and with the project team, because it could be impactful in terms of not just the operation, but also if cam locks are included in the scope, obviously ensuring it's accounted in the footprint. The load bank is required to be tested per NFPA 110 at least once a year. Many of you know that it's also a requirement of Joint Commission, although Joint Commission indirectly requires it as part of their NFPA 110 compliance. They also specifically state in the section identified that it does need to be completed at least once every 36 months and for a minimum of 4 hours. Most often, when the load bank is done, it is done one generator at a time to ensure that if normal source or utility power is lost during the load bank testing, the emergency system or the essential system in a hospital is never jeopardized. From here, facilities, specifically healthcare facilities, also do monthly generator tests. The testing of the generator sets and transfer switches occur under load at least once every 30 days. And this is done for 30 minutes. And what happens is it's initiated the test at typically a different transfer switch at each month. And from here, they don't have a different sequence of operation, but they do go and record all the instrument readings during that monthly test, from everything from the condition of the hoses and the pipes, to the coolant levels, to actually visually inspecting all of the equipment. So it's also important as part of this, we examine what best practices are to help document those sequence of operation. So first, once the sequence of operation that we proposed is reviewed and developed specific for the project, it is important it is documented as part of those project package and drawings. This can be done either directly on the drawings or as a separate narrative. It's important that early engagement is coordinated not just with the facilities team, but also with the utility and any other project impact decision makers, as well as the manufacturers, as different configurations have different impacts on the layout and the configuration of this sequence of operation. Additionally, as indicated in NEC 700.10, dedicated vertical section is required for the emergency and life safety distribution. And this is important to identify because, again, this could impact the layout and the physical dimensions of the equipment. Also, in a worst case scenario, if there is a PLC failure, having manual generator paralleling capability is also an option and recommended on many critical operation facilities. And this is just a last resort to get generators online to support those modes in the event a controller or the generators are not paralleling. It is another level of redundancy for the facility. As described in the sequence of operation, a number of the circuit breakers are motor operated. So it's important to account for the space for those motors, specifically in a switchboard distribution. Whether or not the sequence of operation or the circuit breakers are motor operated at the design intent is important to at least make sure, otherwise there's consideration for space for that to be added in the future. Additionally, the ground fault alarm is required for healthcare facilities for the circuit breakers from that parallel switchgear versus the trip that's required on the service entrance for the same facility. When developing the sequence of operations and parallel switchgear specifications, it's also important that you consider any opportunity to reevaluate the gear as you continue to understand it for the project. One opportunity for doing this is the witness testing. And this is something that is added into the specifications for that parallel switchgear. And it allows the engineer, yourselves, the contractor, and the end user to go to the manufacturing facility prior to arrival on site and review all of the sequence of operation, all of the failure modes, and make any adjustments that may be identified or have been missed prior to the demonstration. It's also important when developing the sequence of operation and the parallel switchgear layout that the arc flash hazard analysis is considered, as well as the AIC rating of the equipment. Many facilities have the capacity to add generators as the facility continues to expand. In this example, it's important to make sure that the AIC rating is properly sized for those future generators as well. As transfer switches get installed as part of the project, it is important that the position they're in is communicated back to the building management system. And this is identified as part of best practice for operation of the facility. So if there is potentially a normal circuit breaker that has nuisance tripping, and the generators are started from that transfer signal because that transfer switch saw a loss of normal power, the facilities team can quickly identify which transfer switch saw that loss of normal power to get that issue resolved. Transfer switches come in different sizes and different types. Two of the types I want to specifically mention is the automatic transfer switch versus the manual transfer switch. The automatic transfer switch, as described, automatically performs the task of going between normal, emergency source, and back to normal. A manual transfer switch requires actual manual operation from a qualified individual to change the position of the transfer switch. Depending on the time or the duration of the outage, if resources don't allow, this could be or force an extended outage for certain systems that are already connected via the manual transfer switch to the generators, delaying or extending that outage and impact. Additionally, when you look at the redundancy of the generators, there's an opportunity many facilities now look at of what's called optional standby mode. This utilizes the redundancy of the generators to be backfed through a circuit breaker interlock system to the normal source, which will operate in an optional standby mode. This minimizes the impact for those spaces and can be identified and coordinated as part of the design and part of the project scope. This allows those spaces, when normal power is out for extended periods of time, to be in business as usual, as it's called, operation. So next, we want to look at a few lessons learned to make sure as these projects are considered and evaluated, that best practice is being applied as well as potential concerns. First, as facilities continue to expand, many of them, as mentioned, get additional generators as well as transfer switches. The ATS controller has a fuse that sends those signals as well as from the parallel switchgear. It's important that as the system changes, the specifications and the functionality within that master control are examined and reviewed to make those accommodations required. Additionally, many of the parallel switchgear configurations have a different combination of too many versus not enough tiebreakers. Depending on how the system is intended to operate, there's the ability to have generator tie distribution generators. And this would allow the system to operate in an A or B bus configuration, but obviously has extended impact in terms of the actual physical space. Next, we want to make sure that any time generators are controlled new with older generators, that the actual genset controllers are identified as part of the project scope. This would include possibly upgrading to the new Woodward controllers to allow that functionality and specifically the communication between the generators for the paralleling. Next, on medium voltage systems, relays have a very effective functionality for added resiliency. It's important to make sure that those relays are not programmed in a manner that disrupt or impact the parallel switchgear functionality and programming. This is usually identified as part of the development of the project, but always important to review on existing facilities. Next, it's worth mentioning and reinforcing the requirement, obviously, for Article 700.10, but also for the life safety dedicated vertical section, as this has an impact on the configuration and physical dimensions of the equipment. Next, on those medium voltage applications, it's important to consider the battery bank, whether it's matching the existing batteries on the facility or whether it's bringing in a new classification of size of batteries, such as 48 volt DC. The battery bank and battery charger and controller also need physical accommodations and is important to be considered as part of the early design phases.
As a construction project comes to a close, the commissioning of the system is very important. First of all, I just wanted to address that it is required by the Critical Operations Power Systems per NEC 708.2. And before the system is even shipped, the paralleling switchgear, it is factory pre-programmed, and this has a lot of everything ready before the commissioning agents and the services technicians are on site to commission the system. As part of the commissioning process, the training of the facilities team to go through each of these functions, they will be involved in this as well. When it is commissioned, it is tested in both an operation mode and a failure mode, and then also too as part of the facilities training to train them to manual parallel the generators if something does not function the way it's supposed to in its automatic mode. One important part is, as we discussed the arc flash settings and breaker coordination earlier, is just to review all of the circuit breaker settings to make sure that they are set to meet all of the arc energy reduction requirements and breaker coordination requirements. Another important part of the commissioning is verifying the grounding of the system meets code and that does not cause any issues between the generators and the paralleling gear and the building ground. One other important thing to check is the alarm indicators to make sure that everything is alarming the way it's supposed to. If there is a failure or something is not working the way that it's supposed to, and that these alarms are also being transmitted back to a building automation system where the facilities team is alerted in the case of something not going right. As far as any automation testing, the tie circuit breaker operations is also run through a commissioning process as well. And as we discussed, the building automation system is monitoring the status of all emergency operations and the ATS positions. This is also verified as part of the commissioning process. A very important part is to review the preventative maintenance plan and to review the complete electrical essential system, including any existing that it is tying into, just to make sure, again, that the facilities team is aware of what they need to do in the long term and understand how the whole system works together. So in wrapping up this presentation, I just wanted to thank everybody for being a part of this, and just to do a quick review of what we discussed today. The sequence of operations for the paralleling switchgear does vary from project to project, and we emphasize this at the beginning, and it is important to customize each sequence of operations and that be included in the construction documents from when they are issued for bid. We reviewed some key terms that you need to be familiar with, as well as define some different load classifications that influence the development of a sequence of operations and the design of an emergency power system. We also dove into an example and showed in some great detail of how to pull together a sequence of operations, discussing intent options of what happens when you lose your normal source of power along with some failure modes. We also discussed some considerations as far as best practices and lessons learned, with some great pointers in there, and wrapped it up with a quick overview of the commissioning of an emergency power system. And with that, I will turn it over to Mark for the question and answer portion of this presentation.
Great, thanks Jeremy and Zach. Now it's time for the question and answer portion of our presentation. Please participate in the live Q&A with your Zoom invite details. These details can also be found in the Additional Resources tab on the left side of your screen.